On December 31, 2025, a date that will likely be referenced in astronomical textbooks for decades to come, the scientific community received the definitive conclusion regarding the most scrutinized object of the year, the interstellar visitor known as 3I Atlas. In a comprehensive announcement that reverberated through both the halls of academia and the public imagination, the Breakthrough Listen initiative released the results of the most sensitive radio survey ever attempted on an object originating from outside our solar system. The findings, detailed in a study led by Ben Jacobson Bell of the University of California, Berkeley, provided a categorical answer to the question that had hung over the object since its discovery. After pointing the colossal Green Bank telescope at the visitor during its closest approach to Earth, the researchers found absolutely no evidence of technosignatures. The radio silence was absolute. However, this was not merely a report of nothing found. It was a scientific masterclass in defining the limits of observation. The data collected was so precise that it allowed the team to place a strict upper limit on the object's potential emissions, confirming that if 3I Atlas were an active extraterrestrial probe, it was transmitting with a power level lower than 0.1 watts, a whisper of energy weaker than the output of a standard consumer cell phone. This result effectively shattered the alien artifact hypothesis for this specific visitor, pivoting the global narrative from science fiction back to the rigorous and equally fascinating realm of cometary physics. The journey to this conclusion began months prior with the discovery of 3I Atlas by the Atlas Sky Survey, a system designed to patrol the heavens for dangerous near-Earth objects. When the object was first flagged, its trajectory immediately set it apart from the millions of asteroids and comets that populate our own solar system. Unlike local bodies, which orbit the Sun in elliptical loops, 3I Atlas was moving on a hyperbolic path, cutting through the plane of our solar system at a steep angle and with a velocity that exceeded the escape velocity of the Sun. It was clear from the mathematics of its orbit that this was a traveler from the deep void, a messenger from a distant star system that had been ejected by gravitational forces eons ago. As only the third such object ever confirmed, following the mysterious Oumuamua in 2017 and the comet 2I Borisov in 2019, 3I Atlas represented a rare opportunity to study the material composition of an exoplanetary system up close. However, the legacy of Oumuamua, which had displayed anomalous acceleration and a strange shape that defied easy categorization, meant that the artificial hypothesis was never far from the minds of observers. The possibility that such an object could be a derelict probe, a listening post, or a piece of interstellar wreckage compelled the scientific community to look beyond mere visual inspection and scan the object for the telltale signs of technology. To conduct this forensic interrogation of the electromagnetic spectrum, the Breakthrough Listen team turned to the Green Bank telescope in West Virginia. This instrument is not merely a telescope, it is a monument to human engineering and curiosity. With a dish spanning 100 meters in diameter, large enough to hold a football stadium, the GBT is the world's largest fully steerable radio telescope. Its location is equally critical. It sits deep within the National Radio Quiet Zone, a federally mandated area where radio transmissions are strictly restricted to prevent interference with scientific observations. In this valley of silence, the GBT is capable of detecting the faint radio whispers of the cosmos that would otherwise be drowned out by the noise of modern civilization. On December 18, 2025, as 3I Atlas raced past Earth at a distance of approximately 1.09 astronomical units, roughly the average distance between the Earth and the Sun, the massive structure of the GBT was slewed to track the object's path across the sky. The timing was deliberate, calculated to catch the object when it was closest to our receivers, thereby maximizing the potential signal strength of any transmitter that might be on board. The observation strategy employed by Jacobson Bell and his team was designed to be as comprehensive as possible, targeting a massive swath of the radio spectrum from 1 to 12 gigahertz. This frequency range is of paramount importance in the search for extraterrestrial intelligence, SETI. It includes the L, S, C, and X bands, a region often referred to as the terrestrial microwave window. In this part of the spectrum, the galaxy is relatively quiet with low background noise from synchrotron radiation and other cosmic sources, and the Earth's atmosphere is highly transparent. It also contains the famous water hole, a quiet band between the spectral lines of hydrogen and hydroxyl, which SETI theorists have long posited as a logical meeting place for interstellar civilizations to conduct communication. By scanning this entire range, the researchers were effectively tuning their radio to every likely channel an alien civilization might use for navigation, telemetry, or contact. The sheer bandwidth of the scan meant that the team was collecting billions of bits of data every second, creating a digital recording of the radio environment surrounding the interstellar visitor. The analysis of this data required the use of advanced computational tools, specifically the TurboSETI software pipeline. The challenge in modern radio astronomy isn't just collecting data, but sifting through it. The Earth is a noisy planet, constantly blasting radio waves into space from GPS satellites, airport radars, television broadcasts, and military communications. To find a potential alien signal, the software had to identify narrowband signals, spikes of energy that occupy a very thin slice of the spectral frequency. Natural astrophysical phenomena, such as quasars or pulsars, are broadband emitters, splashing energy across wide frequency ranges. Artificial technology, by contrast, compresses energy into narrow channels to maximize efficiency and range. The TurboSETI algorithm combed through the terabytes of data collected from 3I Atlas, looking for these needles in the haystack. But the search was further complicated by the physics of motion. Because 3I Atlas was moving at tens of thousands of kilometers per hour relative to the telescope, any signal it transmitted would be subject to the Doppler effect, drifting in frequency over time. The software had to account for this drift, testing thousands of potential acceleration rates to ensure that a genuine signal wasn't discarded simply because it was sliding across the dial. The results of this exhaustive search, as announced on December 31st, were a triumph of negative data. The study concluded that there were no radio emissions from 3I Atlas that could be distinguished from the background noise. However, the true value of the study lies in the upper limit established by this non-detection. The sensitivity of the Green Bank telescope is such that the researchers could confidently state that they would have seen any transmitter with an effective isotropic radiated power of 0.1 watts or higher. To truly appreciate the significance of this number, one must compare it to human technology. The Voyager 1 spacecraft, currently the most distant human-made object in the universe, communicates with Earth using a transmitter that outputs about 20 watts of power. A typical airport radar blasts out thousands of watts. Even the cell phone in your pocket, when struggling to find a signal, can output nearly 1 watt of power. The 0.1 watt limit established by the Breakthrough Listen team means that 3I Atlas is quieter than a cell phone. It implies that if there is technology on that object, it is not merely dormant, it is utterly silent, emitting less radio energy than a child's walkie-talkie. This level of sensitivity effectively rules out any scenario involving an active probe beaming data back to a home star, or a scanning device pinging Earth with radar. This radio silence was the final piece of a puzzle that had been assembling for weeks, corroborating the findings from the optical and infrared spectrum. While the radio astronomers were listening for the hum of machinery, optical astronomers had been watching for the behavior of materials. The article from phys.org highlights that prior to the radio observations, specifically on November 30, 2025, the Hubble Space Telescope had captured high-resolution images of 3I Atlas. These images were pivotal in shaping the scientific consensus even before the radio data was processed. Hubble revealed that the object was wrapped in a teardrop-shaped cocoon of dust, a classic feature of cometary activity. As comets approach the sun, the heat causes their frozen volatiles, water, ammonia, methane, and carbon dioxide, to sublimate, turning directly from solid to gas. This expanding gas drags dust particles off the surface, creating a coma and a tail. The teardrop shape observed by Hubble was a clear indication that the solar wind was pushing against this cloud of dust, shaping it in accordance with the laws of fluid dynamics and radiation pressure. Furthermore, the spectroscopic analysis of this coma provided the smoking gun for a natural origin. The observations detected a distinct greenish glow emanating from the object. In the lexicon of cometary science, a green glow is a specific chemical signature caused by the presence of diatomic carbon, C2, and cyanogen, CN. When these molecules are exposed to the ultraviolet radiation of the sun, they fluoresce, emitting light in the green part of the visible spectrum. This is a phenomenon observed in many comets native to our solar system. The presence of diatomic carbon and cyanogen confirms that the surface of 3I Atlas is composed of complex organic ices, the kind that form in the cold outer reaches of protoplanetary disks. If 3I Atlas were an artificial metal shell or a solar sail, it would not be sublimating carbon gas and glowing green. The combination of the radio silence, proving no active technology, and the chemical spectroscopy, proving the presence of sublimating ices, locks the door on the alien hypothesis. The data forces us to view 3I Atlas not as a scout from a civilization, but as a geological sample from a star system that may have formed billions of years ago. The implications of this finding extend far beyond the classification of a single object. The natural verdict for 3I Atlas supports the theory that the galaxy is teeming with interstellar debris. Planetary formation models suggest that when giant planets like Jupiter migrate during the early history of a solar system, they gravitationally scatter trillions of smaller bodies, ejecting them into interstellar space. These objects then drift through the galaxy indefinitely, occasionally passing through other star systems. The fact that 3I Atlas behaves so similarly to our own comets, outgassing water and carbon, forming a tail and adhering to the laws of gravity, suggests a universality to the process of planet formation. It implies that the chemistry of the universe is consistent. The same ice and rock that coalesce to form the precursors of life on Earth are present in star systems light years away. 3I Atlas is a testament to this cosmic consistency, a frozen time capsule that traveled across the void to show us that our solar system is not chemically unique. However, the Breakthrough Listen investigation was not a wasted effort. On the contrary, the article underscores the operational success of the mission as a proof of concept for future SETI research. The ability to go from the discovery of a fast-moving, unexpected target to a high-sensitivity radio observation in a matter of months is a logistical and technical triumph. In the past, telescope time on instruments like the GBT was allocated years in advance, making it nearly impossible to react to sudden events like the arrival of an interstellar object. The 3I Atlas campaign demonstrated a new agility in the scientific community. It showed that the infrastructure is now in place to rapidly pivot our most powerful ears toward the sky when a visitor arrives. This readiness is crucial because statistical models predict that we will find more of these objects in the coming years, especially with the deployment of new survey telescopes like the Vera C. Rubin Observatory. The next visitor might not be a comet, and the protocols refined during the 3I Atlas study, the nodding strategies, the frequency choices, the Doppler drift algorithms, will be the very tools used to make that determination. The study also highlights the role of collaboration in modern astronomy. The synergy between the optical teams using Hubble and the radio teams using the GBT was essential. The optical data provided the precise orbital ephemeris needed to point the radio telescope, while the radio data provided the check against the optical findings. The lead author, Ben Jacobson Bell, and his team represent a new generation of astronomers who are comfortable working at the intersection of traditional astrophysics and technosignature research. By publishing their null result with such detail and transparency, they have strengthened the scientific rigor of the SETI field. They have demonstrated that the search for aliens is not about wishful thinking, but about imposing strict observational constraints on the universe. A null result is a valid scientific result. It tells us where the aliens aren't, or at least how they aren't communicating, which helps refine the search parameters for the future. Looking toward the horizon, the article concludes by referencing the future of radio astronomy, specifically the Square Kilometer Array, SKA. Currently under construction, the SKA will be an interferometer composed of thousands of antennas, creating a collecting area vastly larger than the Green Bank telescope. When the SKA comes online, it will offer sensitivity orders of magnitude greater than what was available for the 3I Atlas observation. While the GBT could detect a cell phone at 1 AU, the SKA might be able to detect the leakage radiation from a planetary radar or a television broadcast from a nearby star. The 3I Atlas mission serves as a prelude to this new era. It has baselined our current capabilities and highlighted the challenges of filtering out Earth's own radio interference. As humanity builds quieter and more sensitive instruments, and as we develop AI-driven algorithms to process the data, our ability to detect fainter and fainter signals will grow. The silence of 3I Atlas is not a discouragement, it is a calibration point for the instruments that will one day find a signal. Ultimately, the story of 3I Atlas, as encapsulated by the December 31st announcement, is a story of human perspective. We live on a small planet in a vast, quiet galaxy. When a rock from another star falls into our neighborhood, our instinct is to ask if we are alone. We project our hopes and fears onto the intruder, wondering if it carries a message or a watcher. The scientific method allows us to strip away those projections and see the object for what it really is. In this case, the Green Bank telescope revealed that 3I Atlas is a silent traveler, a mute witness to the history of another sun. It carries no radio transmitter, no alien crew, and no message for humanity. But in its silence, it tells us something profound about the nature of our universe. It tells us that the spaces between stars are filled with the debris of creation, and that while we may be waiting for a call, we must also be content to study the stones that wash up on our shores. The most sensitive radio observations found no evidence of technology, but they found ample evidence of human ingenuity, persistence, and the unyielding desire to understand the cosmos. The files on 3I Atlas may be closed, but the sky remains open and the Green Bank telescope continues to listen, waiting for the next visitor to emerge from the dark.